Hello, Flat Earth researchers, debaters, and debunkers. Here's an experiment challenge for pilots or anyone else who is inclined to check whether the globe Earth model fits with what we can observe and measure in reality. And if you are the pilot of an aircraft like this Gulfstream jet, you can do this experiment in about 3 minutes. Or if you want to take longer, then all the better. You'll get more conclusive results, hopefully. All you have to do is fly straight and level. And from the observation and from the measurements made in those 3 to 6 minutes, if you like, we can then determine whether we live and fly on or above a flat, level Earth or fly around a globe. Let's be really clear here what I mean by comparing the globe Earth model with reality and the observations that we see in real life and the measurements we can make in real life. Here you can see a globe Earth with an aircraft above it. Of course, it's not to scale, it's just to illustrate the point. To the left, we have the kind of mathematics that is used for the globe Earth model. So this is an abstract concept. It is a view that we've never ever had of the Earth or us on or above the Earth. But of course we think that we are smart creatures in order to perceive this external reference frame from seeing the Earth from our point of view on or above it, like the photograph we see on the right hand side here that you might see from an aircraft's cockpit with the heads-up display. So that's what we see in reality, but what we perceive and think we are smart being able to perceive but have never actually seen in real life is this external reference frame of a globe. And of course, when you use these mathematical equations and diagrams, the model works in of itself. No one is going to deny that if you draw a line from a point at a certain height above this sphere, that you're going to get an angle that goes down to the horizon and gives us a tangent line that is a certain distance from that elevated point above the imaginary Earth. As a model, it all works out. But is that what we see? And how can we make this experiment to change what we see and compare it to the globe Earth model? Well, first of all, we've got this idea that there should be a horizon that goes down from eye level the higher we get above the Earth, which we can illustrate by putting this diagram on top of this one and showing the tangent line from the pilot's point of view going down to the horizon here. Now, straight away, this reference frame that we have illustrated here with a mathematical model doesn't prove anything at all. Being able to do the mathematics doesn't prove that you live on a globe. It just proves that you can do Pythagoras' theorem and work out what angles and distances should be for tangent lines on that circle or in that model. What we see in reality doesn't reflect this illustration whatsoever. Let's have a look at a couple of examples of that. Here is what I presume to be a real photograph of the surface, at least. The aircraft might be superimposed, but it looks like a fairly natural view. The point being that in about the center of the photograph, we see the horizon at our eye level if we are looking straight ahead, and the two aircraft at the bottom appear to be below or in front of the horizon. So that would of course indicate that they are lower than us physically. But the point being is that in reality, we see this horizon beyond and above the aircraft. Whereas if we compare that to the model that we are looking at here, then the aircraft is way above the surface. It has to be illustrated like that to fit with the mathematical model, but that doesn't fit with the way we see things in reality when we look at a photograph like this or a photograph like this. Or we can look at photographs from the cockpit through a heads-up display. And this kind of image is often a bone of contention when arguing with pilots that believe they are navigating above a globe, because in the heads-up display we see this horizontal line here which basically represents the aircraft's level, and it is also the same as the artificial horizon that's located on the instrument panel of the cockpit. And this is something that we need to use for the experiment, as well as the altimeter, which is also on the instrument panel but displayed here as well, showing us that we're at 45,000 feet. So we're quite high above the Earth, and this gap that we see between the horizon line and the real horizon in the distance could be claimed to be evidence of curvature, because we see a drop of the horizon that would appear to correlate with the globe Earth model. But we've got to think about what we're actually seeing here, whether this horizon is in the center of the field of view of the camera itself, but also the fact that this symbol here shows us that the aircraft's nose is pitched up from level, or its own level, and it would have to do this to fly straight and level. So we can assume that it's doing this to fly straight and level, because at this high altitude of 45,000 feet the air is less dense, and so the aircraft has to pitch up in order to travel in a straight horizontal line known as flying straight and level. So no, the nose won't be pitched forwards, it will be pitched up in order to maintain that level flight. So this is a normal attitude for the aircraft when it's flying straight and level. So of course in this case the horizon will appear below the horizon line on the heads-up display. Now, even if the information of the heads-up display is done based on a globe model, this fact that the aircraft will be pitched up at this altitude with this air pressure will be factored in to the calculations that are done to project this image on here. So even if the heads-up display information correlates with the globe Earth model because of the height above the Earth and where we see the horizon in relation to the aircraft's level, this can all just be assumed. It doesn't necessarily mean that that's what's happening in reality. So how can we test this in an aircraft in 3 minutes? Let's go back to our experiment outline and just recap what we're looking at here. We have the aircraft above an imaginary globe Earth that we can only see or perceive in this external reference frame that we've never seen in real life. On the top right we have a photograph as if looking out of the cockpit, and it has a heads-up display. Down here below that we have an artificial horizon, and for this experiment the idea is to keep the artificial horizon where it is, keep it level, keep it horizontal. And again, bearing in mind that this is just a display to represent the aircraft's level. It has no relationship with the Earth beneath it. It's not a superimposed image like the one on the heads-up display. We just have something representing the surface and the sky so that we can show where the aircraft's level is in relation to that. And so it doesn't matter how high the aircraft is above the Earth with an artificial horizon, it won't show an increasing gap. It will just show the aircraft's level. So by keeping this level while we fly straight and level, then we should see the horizon, or point B in front of us, drop as we move forwards. And the further we go forwards, the further it will drop, until eventually we've gone over that point that was our horizon a few minutes ago. And of course, what should happen to the altimeter is that we should see an increase in altitude. Now, again, I've got to stress that this is, of course, not to scale, but we should be able to see some kind of results. And the kind of results we can expect from this aircraft, which is a Gulfstream. G650 that has a cruising speed of 956 kilometers an hour. And so if you travel just 50 kilometers, then what you should see and be able to measure with the altimeter is a curvature drop of almost 200 meters, or 186.2 meters to be precise. And to do that should only take, according to my calculations, only 3 minutes and 8 seconds. Yeah, so these figures have been worked out from curvature calculators and what have you. But if you're traveling at cruise speed, again with your nose up or whatever it is, it doesn't matter. Wherever you start your experiment, whatever the reading or the whatever you see on the heads-up display or through your cockpit window should indicate to you that the horizon is dropping away as you travel forwards. Let's just have a quick look at what I'm talking about here. Here's that view that we had put up in the top right hand corner of our experiment outline, and I've superimposed a heads-up display on here, just showing you what we should see. As I said, the horizon line is point B, our tangent point according to the globe Earth model, and so in reality, if we carry on flying straight and level, we should see this horizon drop further and further away from where it was when we started the experiment 3 or 6 minutes ago. It's as simple as that. So that's the challenge. Can a pilot fly straight and level for a few minutes above the Earth and see whether the observations and the measurements that can be made fit with the globe Earth model? A model that we've never seen and can only ever perceive. But maybe it's possible now to actually try and measure it. Thank you very much. Click subscribe and the bell icon if you'd like to receive notifications of new videos from Phuket Word.